highly tilted to their planet's equators, are called irregular moons. Most of these move in retrograde orbits, clockwise if their planet rotates counterclockwise. Phoebe, the newly discovered moon orbiting Saturn, is a perfect example. She began her celestial life as an independent traveler, orbiting the Sun before being captured by the more massive Saturn. Whether regular or irregular, moons must fall within the gravitational reach of their parent planet. The limit of these orbits is known as the heliosphere. This phenomenon is named after George William Hill, an American astronomer from the mid-1800s.
So a heliosphere is this region around the planet that moves along with the planet, inside of which the gravity of the planet overwhelms the gravity of the Sun.
The moons of Mars, Deimos and Phobos, operate very differently within the heliosphere.
If the planet is rotating faster than the moon it orbits, like Deimos, the tidal forces between the two actually shove Deimos out further and further. Phobos, on the other hand, is rotating faster than Mars rotates.
These small moons were discovered by American astronomer Asaph Hall in 1877. He named Phobos after the Greek god of fear and Deimos for the god of terror. Tom Duxbury was part of the Mariner 9 mission that first photographed the two potato-shaped moons in November of 1971.
This was late at night in a cold, rainy, dark, dreary day, and I looked at this and I turned the picture sideways. It looked like a skull. And it was such an eerie thing.
Phobos is in a death spiral. It orbits just 3,700 miles from the Martian surface, closer to its host planet than any moon in our solar system. If our own moon were as close to the Earth as Phobos is to Mars, it would look 20 times larger.
Its orbital period would be in hours, not days like it is now, but hours. And at full moon, it would fill the sky.
The daily tides, would rise and fall tens of feet, if not hundreds of feet. And so the Earth's moon would eventually crash into the Earth in such a situation.
Phobos's predicament is caused by a process known as secular acceleration. As Phobos races faster than Mars rotates, a tidal bump is raised on the Martian surface. In the process, Mars yanks Phobos closer to its surface with each orbit. The struggle between Mars and Phobos is similar to the dynamics of a simple game of tetherball. Imagine the ball as the moon, the pole as the planet, and the rope between the pole and the ball as the planet's gravitational pull.
What we see is that the gravity would pull the moon in such a way that it speeds up. It goes faster and faster, and it works its way until it eventually hits the pole. That's exactly what's happening to Phobos. Phobos is going around Mars faster than Mars rotates. That tidal interaction is pulling Phobos in closer and closer and speeding it up in its orbit. In about 50 million years, we expect Phobos to be pulled in so closely it will impact Mars and disappear as a moon of Mars. On the other hand, Deimos, the further out moon, is going slower than Mars rotates. And so it's unwinding the string in the opposite way. And what we see is Deimos is going further and further away from Mars. And eventually Deimos will be pulled away from Mars by the gravity of the Sun. So over time, Mars will become moonless.
Because Phobos outpaces the rotation of Mars, it appears to rise in the west and set in the east.
Instead of the planet turning quickly under it like our moon and most other moons, and thus having it rise in the east and set in the west, it races ahead of the rotation of the planet, and so it comes up on the western horizon and races ahead and sets on the eastern horizon.
It will be another 50 million years before Phobos completely disappears. Before then, it may prove useful for the eventual colonization of Mars. Science fiction writer Arthur C. Clarke speculated on this idea in his book, The Sands of Mars. Although there is no real reason to colonize Phobos itself, its close proximity to Mars makes it a natural way station.
From a gravity standpoint, it's much easier to go to Phobos, which has no gravity, than it is to fight the gravity of Mars to get down to its surface.
From Galileo to Stanley Kubrick, the giant planets of the outer solar system have tantalized our imagination with their enormity. But in reality, exploring them is tantamount to suicide. The overwhelming pressure from Jupiter's massive atmosphere would make it almost impossible to function. But the moons of these behemoths may provide a more promising platform for exploration and even future colonization. Are these prisoners of Jupiter's gravity, hostile worlds with little chance of sustaining organic life? Or might they provide a safe haven for future generations of planetary explorers? Until recently, very little was known about the moons of the gas and ice giants. Most of them remained hidden in the glare of their parent planets. Today, modern telescopes and unmanned space exploration reveal a realm populated by a host of moons, from planet-like spherical worlds to misshapen ones barely 30 miles across. Jupiter, the largest planet in the solar system, is a moon magnet. Nearly 4.5 billion years ago, it began as a massive gas cloud collapsing in on itself. This process, known as accretion, formed the beginnings of the Jovian system. While nearly all the gas and spinning material went into forming Jupiter itself, a very small percentage clumped in small eddies within Jupiter's orbit. These miniature accretions solidified into Jupiter's regular moons, Io, Europa, Ganymede, and Callisto. As Jupiter coalesced, its massive gravity began adding to its menagerie, little remaining bits from the birth of the early solar system.
The giant planets formed early in a gas-rich environment when there was lots of little flotsam and jetsam around the solar system still to be captured into orbit.
The number of Jupiter's moons ranges from 60 to over 200, depending on who's counting. What's clear is, if you could stand at the edge of Jupiter's gaseous atmosphere and look to the heavens, you'd see a magnificent dance of lunar objects.
It would look pretty cool to be able to see the moons. Every so often you'd see Io come by. Every second time Io comes by, you'd see Europa at the same time. And every 4 times Io comes by, you'd see Ganymede.
One member of this Jovian cast is so battered by Jupiter's great mass that it's literally bursting from the inside out. In February of 2007, the New Horizons spacecraft, eventually bound for Pluto, focused its cameras on Io. About the size of Earth's moon, it orbits 263,000 miles from Jupiter's surface. What sets Io apart from the other Jovian moons is its spectacular volcanism. New Horizons cameras captured detailed photos of glowing lava scattered across Io's surface. A huge 200-mile-high dust plume rose above the surface of the molten moon. Io, like all Jupiter's regular moons, is named after a lover of the god Jupiter from Roman mythology. It was discovered by Galileo in 1610. First photographed by Pioneer 1 in 1974, and again by Voyager 1 in 1979, its pulsating activity has puzzled and intrigued scientists for decades.
Leaving Io is about a ton per second of material. Every second of every day. It's a phenomenal machine.
I would like to go to Io, even though it would be very dangerous and hot and sulfurous.
Io is too small to have maintained a molten core since its formation. Another mysterious process must be responsible for its heating.
Io's entire interior may be molten because it's squeezed so much as it's orbiting around Jupiter.
This process is known as tidal heating. The massive gravity of Jupiter is causing friction at the inner core of Io. Much like a sculptor needs a cold lump of clay, Jupiter is endlessly creating its own masterpiece.
If a moon gets a little bit of tidal heating, it becomes malleable. It can be stretched out like clay and deformed by the gravity of the parent planet. The surface of the moon is cold. It breaks, like pulling clay apart quickly. It'll break. But the interior, where it's warm, can literally flow and stretch and be kneaded by the gravity of the parent planet.
Most regular moons have circular orbits. To produce tidal heating, a moon must be in a more oblong orbit, where the distance from the host planet changes radically during a single revolution. The only way to produce these eccentric orbits is if another moon's gravity disrupts it.
When a moon is in an eccentric orbit, a non-round orbit, it gets closer and farther from its parent planet. When it does, it gets squeezed, it gets pulled apart when it's closer.
Io is in orbital resonance with its companion moons Europa and Ganymede, while Jupiter and Io struggle to find a synchronistic relationship. Europa and Ganymede are yanking Io in opposite directions. Jupiter yanks back, and Io gets stretched and squeezed in the process. The tidal heating on Io, which is responsible for its prodigious volcanoes, has a secondary side effect. It creates the largest stationary visible object in the solar system, a massive gas cloud